Good day friends, welcome to my channel lecture series on power electronics. In this lecture, we will be seeing the operation of a single phase full wave bridge rectifier, especially the controlled full wave bridge rectifier. Rectifiers convert AC to DC, that is a bidirectional input is converted into a unidirectional output when rectifiers are used. They are classified as uncontrolled rectifiers and controlled rectifiers. It is called as an uncontrolled rectifier when diodes are used. It is called as controlled rectifiers when thyristors, especially SCRs, are used. Rectifiers are classified based on the input supply as single phase or three phase, based on the quadrant of operation as one quadrant, two quadrant or four quadrant. Based on the number of pulses available at the output, it is classified as 1 pulse, 2 pulses, 6 pulses or 3 pulses. Here in this lecture, we will be knowing about the operation of a single phase, 2 quadrant, 2 pulses rectifier. Rectifiers are used mostly in DC motor speed control. If a variable input DC is required for a DC motor, it can be obtained from a rectifier. DC supply for inverters. Inverters convert DC to AC. The input to an inverter can be from a rectifier. Then in electrochemical processes also it is used. DC traction. Traction means in the railways. HVDC transmission, high voltage DC transmission. In all these applications, rectifiers are used. This is a basic circuit of a single phase full wave controlled rectifier. The name is controlled rectifier because we are making use of thyristors here, SCRs here. There are 4 thyristors. The numbering is given as T1, T2, T3 and T4. The input is AC, output is connected to a load. This load can be a resistive load or RL load, or it can be even a motor. So in this circuit, we have shown a resistive load. Let us see the operation of it. Thyristor will be forward biased when a positive is available to the anode, negative is available to the cathode. So during positive half cycle, at this junction, the voltage is going to be positive. Here it is going to be negative. So this positive here will make the T1 forward biased. The anode is getting plus over here. The cathode is getting plus. So T4 is reverse biased. T1 is forward biased. Here when it is minus, the T2 thyristor is getting forward bias because negative is available to the cathode. And here if we see T3 is reverse bias because negative is available to the anode. So during positive half cycle, this junction is positive and this junction is negative. During negative half cycle, this junction is negative and this junction is positive. We see in this picture, during positive half cycle, T1 and T2 will conduct if the gate pulse is given. They are already forward biased. So when the gate pulse is given, the current flow will be from the supply through T1, through the resistive load, through T2, back to the supply. During negative half cycle, this junction becomes negative, this junction becomes positive as already mentioned, because T3 and T4 are forward biased. If at this time the gate pulse is given for T3 and T4, the current flow will be from the supply through the point plus, through T3, through the resistive load, through T4 back to the supply. The current always flows from plus to minus. So if we compare these two diagrams, in the first case during positive half cycle, the current flow in the load is from top to bottom in the resistive load, that is in this direction. If you see in the negative half cycle also, the current flow is from top to bottom. So from a bidirectional input, we are able to get a unidirectional output. So by properly giving the gate pulse to T1, T2, then switching them off giving to T3, T4. From a bidirectional input, we'll be able to get a unidirectional output. We see the voltage and the current waveforms. During the positive half cycle, T1, T2 conduct. During negative half cycle, T3, T4 conduct. Of course, during negative half cycle, we get the current in the same direction in the load. And if you see the current waveform, it looks similar to the voltage waveform, except that the amplitude is reduced. If the firing pulse is given at the 0th instant, we get a full pulse. And if the firing angle is given at a later stage, we'll get only the part of the pulse as shown in this diagram. So if the firing angle alpha at some value of alpha only, the current is flowing through T1 and T2. So the voltage waveform is starting from here only. Here we are getting an amplitude which is different from that of the full firing angle. The values of the average output voltage can be obtained using the formula VDC is equal to 2 Vm by pi into cos alpha, where alpha is the firing angle. IDC can be obtained by dividing the VDC by the resistance value. RMS value of the output voltage can be obtained using this formula. Vm is the maximum value of the voltage. Vm by R into 1 by pi is pi minus alpha plus half of sine 2 alpha root of it. RMS load current can be obtained by Vrms by R. So in this lecture we have learned the operation of a single phase fully controlled rectifier. Thank you.